This is the 15th video in a series devoted to differential equations, and we've just done a lot with second-order differential equations, so it's finally time to look at an application to linear second-order differential equations. And the application that we'll focus on is the modeling of a spring system. So let's see the setup. So let's consider that we have an object with mass m suspended by a spring. So that's going to obviously pull the spring down. And if there's nothing going on there, that spring will be at rest. And so let's call that position at rest the equilibrium. So I've got that here. So if the object is at rest, we say it is in equilibrium. Next, we'll set the function y of t to be equal to the displacement of this object from equilibrium at time t is bigger than 0. So we're modeling this for positive time. So here's an idea of the picture of what's going on here. So I've set the equilibrium point to y equals 0, and so that would be this t-axis. So just to really think about what's going on here, let's maybe box over here. And if there's nothing going on with the spring, then it's just kind of peacefully hanging at equilibrium. So it would have a picture like that. But let's suppose that we pull this mass down a little bit and then let go. Well, then the spring is going to pull it up through this equilibrium position to some sort of high point. But once it reaches this high point, it's going to fall through the equilibrium position down to another low point, and then it's going to continue that over and over again. Now, in the real world, that oscillation would stop due to like friction or air resistance or something. Okay, so our main goal for this video is to describe the function y of t. In other words, find exactly what this function is. And we can do that by building a differential equation out of the forces acting on this object. So there are four main forces acting on this object. The first is the force due to gravity, which is pulling this object down. So this will have a value of minus m times g, where m is the mass and g is the acceleration due to gravity depending on your unit system. So if we're meters per second, it would be 9.8 meters per second, but we would maybe just round that to 10 to make the calculation easier. And then if you're in feet per second or miles per hour, then it might be something different, but generally we'll keep to the metric system. Okay, then we'll have this spring resistance to changing the length. So this is the resistance that you feel when you pull a spring. And so we'll call this force F sub s, and this force will be equal to K times delta L. And so delta L is the difference between the length of the spring and the length of the unweighted spring. And then K is something called a spring constant. And now I'd like to point out that we can rewrite this F of s or F sub s as K times delta little l minus y. And that's just rewriting this delta capital L as this delta little l minus y. And what's this delta little l, you might say? Well, this is the distance from the equilibrium. So let's write that down. So distance to equilibrium. So if you subtract the distance to the equilibrium and the current displacement, then you get the difference in the spring's current length to its natural length unweighted. Okay, so we could multiply this out if we wanted to, and this would be K times delta L minus K times Y. So that's our force F sub s, which again, like I said, is the spring's resistance to changing length. And then I said this verbally, but let's maybe point it out here. This K right here is called the spring constant. And we'll actually be able to calculate that, in the next few minutes from some other givens, but we don't quite have that yet. Okay, so now let's talk about the damping force. So this is the force that is motivating the spring to stop its oscillation. So this would be like due to air resistance, or it would maybe be due to friction or something like that. So notice air resistance and friction will increase as the velocity increases. And the velocity is the derivative of the displacement. So that being said, we can say that the damping force is proportional to the velocity. So we can say this F sub d, the damping force, is minus c times y prime. And it's negative because it's acting to decrease the displacement of the spring. And then we've got an external force, and this is just going to be a function f of t. And this could be like something that's moving into the spring. And this is some force that's acting on the object. And this could come from a number of different places. Okay, so now let's put all of this together along with Newton's second law of motion, which says force equals mass times acceleration. So that means we can set up a nice equation. So mass times acceleration of the object is m times y double prime, given that acceleration is the second derivative of displacement. So like I said, this is going to be equal to the force, but then the force will be the sum of all of these forces over here. So that'll be all of the forces acting on the spring. So let's add these up. We have minus m times g, and then we have plus k times delta L minus k times y, and then we'll have minus c times y prime, and then plus f of t, where that's our external force. And now we'd like to make a simplifying step here. And let's suppose that we have the setup where y is identically 0. So that means that you were to add a weight to a spring and you would let it settle until it's not moving at all. Okay, so that's something that will happen. So if y is identically equal to 0, then that means that y prime is obviously equal to 0 and y double prime is also identically equal to 0. Furthermore, let's also look at the case when f of t is identically 0. Because if the object is peacefully settled at the bottom of this spring, we can assume that there's no external force. Okay, so plugging that into our above equation, we'll cancel everything out until we have 0 equals minus mg plus k times delta L. But look, we can solve that for the spring constant, and that's really important. So we have k equals m times g over delta L. So in other words, we have an equation for the spring constant in terms of the mass, the force of gravity, and the difference between the length of the unweighted spring and the spring at equilibrium. So let's maybe be sure to write out what this delta L is so we're totally clear with what it is. So this is the difference between the length of the unweighted spring and the length of the weighted spring at equilibrium. So often you'll be given this number, and given that delta L number, you'll be able to calculate our spring constant K. Okay, so this blue boxed equation pushing over to that pink boxed equation allows us to find our spring constant, but looking down here at this equation, which I'm boxing in orange, also gives us this simplifying effect. So notice minus mg plus kl equals 0, and we've got minus mg plus k delta L here. So that means this orange boxed equation goes off to 0, which is nice because now we've got something fairly simple. We've got a constant times a second derivative, a constant times a first derivative, and a constant times the original function or the 0th derivative, and then a forcing function. So rearranging this, we've got the nice differential equation which will describe this system. So we have my double prime plus c times y prime plus k times y equals f of t. Great. So now that we have that, let's maybe bring that summarized over here, and we'll look at some important specific cases of this. So here's a summary of what we had on the last board. So the displacement of our object from equilibrium was described by the following second-order linear differential equation with constant coefficients, which may or may not be a homogeneous linear equation. And that is my double prime plus cy prime plus ky equals f of t. Let's recall that m is the mass of the suspended object, c is a damping constant, and k is the spring constant. And we could either be just given the spring constant, or we could calculate the spring constant as m times g over delta L. And let's recall that delta L was described on the last board. It was the difference between the length of the unweighted spring and the length of the weighted spring at equilibrium. Okay, and then finally, capital F is the external force. Okay, we're going to look at the simplest case of this first, and that will be if we have undamped motion and no external force. So this is sometimes known as the simple harmonic oscillator. And so undamped motion means that c is equal to 0, and no external force means that our function f is identically 0. Okay, so in this case, our differential equation collapses to my double prime plus ky equals 0. Which it's like pretty obvious that we would maybe want to write this as y double prime plus k over m times y equals 0. And then notice that k and m are both positive, so this looks to have solutions that involve sine and cosine and no exponential part by our previous knowledge of these types of equations. Now I'm going to introduce some notation. So let's set omega naught equal to the square root of k over m. And notice now our differential equation looks like y double prime plus omega naught squared times y equals 0. And like I said, we know the solution to this type of differential equation by work that we've done in previous videos. In fact, we solved a differential equation like this several videos back at this point. So that'll give us the following solution. We'll have y is equal to c1 times cosine omega naught times t plus c2 times sine omega naught times t. Okay, great. And now this may seem like a decent place to end this because we've got a general solution, but in fact there's a more natural way to write this solution. But that's going to involve building some more notation. So let's set a number capital R equal to the square root of c1 squared plus c2 squared. And then with that definition, we can find an angle phi. So I'll say this is phi, and maybe it's from 0 to 2 pi, such that we have c1 equals r times cosine of phi, and c2 is equal to r times sine of phi. And so that's just possible by the definition of R right here. And this is essentially taking the rectangular description of these constants C1 and C2 and making a polar description of these constants. So you can think about all this happening within the C1, C2 plane, and then this is between in the R phi like polar plane. Okay, so anyway, let's see what that leaves us with now. Now we have y is equal to r times cosine of phi times cosine omega naught times t plus sine of phi times sine of omega naught times t. Notice because r is a factor of the C1 expansion and the C2 expansion, I can factor it out of the entire thing. But now there's a trig identity which can help us reduce this thing which has the blue underline. So I'll just put right here, there's a trig identity. So if you don't remember this immediately, then you can look up the page of trig identities either in the cover of your textbook or the Wikipedia page or something. You don't really need to have these identities memorized, you just have to know that they exist and have a good place to find them. So that trig identity will allow us to write y as r times cosine of omega naught times t minus phi. Great, so it's a difference formula for cosine. And then I'd like to also point out here that we've got some names for r and phi, and those names are pretty obvious by this way of writing y. Notice that r is the amplitude of the wave that's describing this displacement. And so this just comes from maybe some stuff you learned in a trigonometry class. And then phi is known as the phase angle. So I'll write that phase angle. It's like the phase shift, if you will. And furthermore, omega naught is key to defining the period. So notice that this will repeat every time that omega naught times t cycles through a period of 2 pi, which means t has to cycle through a period of, let's see, 2 pi over omega. So that's what we'll set equal to capital T, 2 pi over omega, and this is the wavelength. Again, this is just standard stuff from like a trigonometry class. Now, let's talk about how we can define phi in terms of maybe our starting things C1 and C2. Because if you're given like initial conditions, you'll probably want to solve for C1 and C2 using this form. So notice that we can take the quotient of these two equations, and that'll give us something like tangent of phi equals C1 over C2. And you might be tempted here to say that phi is the inverse tangent of C1 over C2, but that would not really be the greatest thing to do because it's going to depend on the sign of C1 and C2. So I'll just put here that this is a defining property of phi. Keeping in mind that if the numerator is positive and the denominator is negative, that gives you something different than if you have vice versa, based on the sign of the SIGN of cosine phi and sine phi. So I'll let you think about that as well. Okay, so maybe if we were to box the takeaway here, it would be all of this down here. So this is like a nice wave equation for the simple harmonic oscillator. Okay, so now let's look at the next case where we are still undamped, but we may have an external force. Now we're going to look at the case where we still have an undamped oscillator, but we have an external force that is of a particular form, and that's F naught over m times cosine omega t. And you might say, well, why aren't we doing this in general? And the answer is because we've done it in general already when we solved non-homogeneous second-order linear differential equations like this. We had several strategies for that. We had undetermined coefficients, we had variation of parameters, we had reduction of order, and so on and so forth. And we're choosing this special case for our forcing function, our external force function, because it's kind of a standard external force and it provides a nice result. So let's look at the differential equation in this case. We have y double prime plus omega naught squared times y equals F naught over m times cosine of omega t. So I've already done my change using omega naught is what, k over m, well, the square root of k over m. Okay, so we'll look at two subcases here. So let's say case number 1 is the case when omega is not equal to omega naught. Okay. And that's an important case because now the homogeneous solution is not this forcing function. Because this forcing function is not one of the homogeneous solutions. In fact, we can just write down the homogeneous solution. So y sub h is equal to C1 times cosine omega naught times t plus C2 times sine omega naught times t. Great. And then to add maybe a little bit more here, let's say our initial displacement is 0. So that's our displacement from equilibrium. And our initial velocity, y prime, is also 0. So how you want to think about this, so it's resting at the bottom of the spring in equilibrium, so that would be this condition, and it's not moving, so that would be this second condition. And then we exert this external force and see what happens. So maybe the external force is like you tap the bottom of the spring, or maybe the external force is some sort of large sound wave or something like that. Okay, so let's maybe find our particular solution using the method of undetermined coefficients from this point. So our particular solution should have the form A times cosine omega t plus B times sine omega t, where A and B are to be determined. Those are our undetermined coefficients. Okay, so if yp is equal to that, we can easily find yp double prime. I'll skip yp prime because that's fairly simple calculation. That'll give us something like this. Omega squared, or maybe minus omega squared, and then A times cosine omega t plus B times sine omega t. In other words, we have minus omega squared times our particular solution yp. Okay, good. So now let's plug this up here and see what we have. So we'll have, like I said, minus omega squared times yp, so that's from our second derivative, plus omega naught squared times yp, that'll be from this portion right here, equals f naught over m times cosine omega t. Great. And now note that we can factor out this left-hand side a little bit. That'll leave us with something like omega naught squared minus omega squared times yp. So in other words, we'll have omega naught squared minus omega squared times A cosine omega t plus B times sine omega t. So that's just expanding our yp, equals f naught over m times cosine omega t. Great. And now we'll use the fact that cosine and sine are linearly independent functions. That means the coefficient of sine right here must be equal to 0. And then we can equate the coefficients of cosine from both sides of the equation. And that gives us the following solution for A. So notice A will be f naught over m times omega naught squared minus omega squared. So that's just by dividing by this term right here. And then plugging this back into the format for our particular solution, we have y sub p is equal to A over m times omega naught squared minus omega squared times cosine of omega times t. Great. So let's bring that up and then we'll continue this example. Okay, on the last board we found the particular solution to our differential equation. I think there might have been a small typo. Justin should have put a note on the screen when it happened. Here we have yp is f naught over m times omega naught squared minus omega squared times cosine of omega times t. But let's recall that our general solution will be a sum of these two solutions. So here we'll have c1 times cosine of omega naught times t plus c2 times sine of omega naught times t plus f naught over m times omega naught squared minus omega squared times cosine of omega times t. Now let's start imposing our initial conditions. So the first is that y of 0 equals 0. So if we plug 0 into this, we'll use the fact that cosine of 0 is 1 and sine of 0 is 0. So that'll cancel this one out and give us 1 times c1 for this one, and let's see, just that constant for that one over there. So in the end, we'll have c1 plus f naught over m times omega naught squared minus omega squared equals 0. We can easily solve that for c1, and we'll see that c1 is equal to f naught over the mass times omega squared minus omega naught squared, where I changed the order of subtraction to make up for the fact that I moved it to the other side of the equation. Okay, now I'm going to leave it as a little bit of an exercise for you. This is really straightforward, and that is that this other initial condition, y prime of 0 equals 0, implies that c2 is equal to 0. And that's because if you take the derivative, you get a sine term here. You get a sine term here. Those are both 0 when we set it equal to 0. And we get a cosine term here. But that cosine term only has a C2 out front. So anyway, the C2 is equal to 0. So that means we can write down our most general solution in the following form, keeping in mind that C1 here is essentially the same as this with a changed sign. So let's maybe write this down. We've got that y is equal to f naught over m times omega naught squared minus omega squared. And then we will have, let's see, cosine of omega times t minus cosine of omega naught times t. So this comes from the homogeneous portion. This comes from the particular solution. Notice this is attached to a minus sign because C1 has a different sign from that number right there. Okay, good. And now we'll make a simplification via a trig identity here as well. This is a trig identity that you can look up just as I said before. And what we'll end up with is the following. We'll have y is equal to 2f naught over m times omega naught squared minus omega squared. And then we'll have the product of the following two sine functions. We'll have sine of omega naught plus omega over 2 times t. Good. And then we'll have the sine of omega naught minus omega over 2 times t. Great. And that would be a nice final solution for this undamped harmonic oscillator with the following forcing function. And this is still in the case when omega is not equal to omega naught. So now let's visit the case when omega is equal to omega naught. Like I said, now we're going to look at the case when omega is equal to omega naught, which means we have to take a different format for our particular solution. So yp in this case should be of the form t times a cosine of omega times t plus b times sine of omega, let's maybe call this omega naught times t. And then we'll replace this omega with omega naught up here. Okay, so now let's take the second derivative of yp. I'll skip taking the first derivative. So we have yp double prime will be equal to, we'll have 2 times minus a times omega naught times sine of omega naught times t, and then plus b times omega naught times cosine of omega naught times t. And then we'll have t times the second derivative of what's going on in here, but that actually simplifies quite a bit to minus omega naught times yp. So I'll let you guys check the details. And if you're wondering maybe how I'm quickly taking these second derivatives, there's actually a little bit of a rule here. Maybe we'll fit it in the margin here. If you take fg double prime, that's the same thing as f double prime times g plus 2 times f prime g prime plus f times g double prime. In fact, the derivatives, the higher derivatives expand kind of like binomials, actually exactly like binomials. So that's why we only have a couple of terms here, because the second derivative of t is 0. So that would be like our f double prime term here. Okay, so now let's add yp double prime with yp, and note that this will cancel this based off of our construction of our differential operator over here. So we have yp double prime plus omega naught squared yp will cancel down just to this stuff right here. So we'll have minus 2 times a times omega naught sine of omega naught times t plus 2 times b times omega naught times cosine of omega naught times t. But then we need to impose that that's a solution to this differential equation. That gives us f naught over m times cosine of omega naught times t. Next up, we'll use our favorite trick that the sine and cosine function are linearly independent, so we can equate coefficients of sine and cosine on both sides of the equation. There's no signs on the right-hand side of the equation, so that means that is 0, and we can equate 2b omega naught with f naught over m. And that easily allows us to solve for b. So we have b is equal to f naught over 2m, and we've got the following general solution to this differential equation. So we'll have the particular part plus the homogeneous part. So notice the particular part will be something like f naught times t over 2 times m times sine of omega naught times t from this particular solution, and then plus c1 cosine of omega t plus c2 times sine of omega t. And then I'll let you calculate c1 and c2 based off of these initial conditions. That's a fairly simple exercise. So what I'd like to notice here is that the amplitude continues to increase as t gets larger and larger and larger. So we have some sort of picture like this for our function. So it's going to be bound between these two lines, which are going to be plus and minus these guys right here. So y equals plus minus that, and then we're going to bounce between those two lines. And that's of course if c1 and c2 are equal to 0, so that's like a general format of what's going on here. So this is sometimes called the resonance frequency. And if you've ever seen like old videos of like bridges or other architectural structures like collapsing under wind because they just start shaking faster and faster and faster, that's because they've reached this resonance frequency, which causes the oscillation to just increase in amplitude kind of without bound. So maybe Justin will put one of these like old videos on the screen right now that you can check out. For our last example, we'll focus on the case when we have damped motion, but we have a free vibration. So in other words, there's no forcing function, there's no external force. And so redoing this with an external force is really similar to other things we've done previously in the course, so we won't worry about that so much. Okay, so let's notice that in this case we have the following second order linear differential equation with constant coefficients that is a homogeneous equation. So we've got my double prime plus c times y prime plus k times y equals 0. And this thing has a corresponding polynomial equation, m times r squared plus c times r plus k equals 0. And we can calculate the roots of this with the quadratic formula. And those roots will be minus c over 2m plus the square root of c squared minus 4 km over 2m, and r2 will be minus c over 2m minus the square root of c squared minus 4 km over 2m. Great, so we'll have those two roots. And now here we'll look at a couple of cases. So our first case will be if the system is underdamped, and that will be c squared minus 4km is less than 0. So in other words, we've got a negative under this radical, which means we've got complex conjugate roots. So let's notice that this is equivalent to saying that c is less than 2 times the square root of km. And like I said, this is underdamped. And also, like I said, this has complex conjugate roots, and those roots are of the form minus c plus 2m. So I'll just put r is equal to minus c plus 2m plus minus I times omega 1, where omega 1 is equal to the square root of 4km minus c squared over 2m, where I use this I to switch the order of subtraction right here. Okay, so in this case, we can pretty easily write down like a final solution, and that would be like this. So we'll have y is equal to e to the minus c over 2m times t. So that would be like our exponential part. And then we'll have c1 cosine of omega 1 times t plus c2 times sine of omega 1 times t. So we've got some sort of picture like that. And then if we wanted a graph here, well, we would graph this exponential function. So we would graph maybe it and its copy like this, just kind of for asymptotes. And then we've got this trigonometric function bouncing in between that as it decays. Okay, good. So now let's look at our second case where this is greater than 0. Now we're going to look at the case where our system is overdamped. So in other words, c is larger than 2 times the square root of 2m. But that means that r1 and r2 are distinct real roots. And let's also notice that they're most definitely negative. So we have this is on the interval -infinity to 0. So I'll let you guys check that, but that's pretty easily just by looking at the analysis of these two roots right here. Okay, so that means we've got a solution of the form c1 e to the r1 times t plus c2 times e to the r2 times t. So it's a linear combination of two exponentially decaying functions. So the general graph here will just be of exponential decay. Although this is only a really good model if C1 and C2 are both positive, and that's going to, of course, depend on the initial conditions. Okay, so now let's move into case 3, which is our last case. And that'll be the case when we are so-called critically damped. So critically damped, and that would be when c is equal to 2 times the square root of km, which means we have a repeated real root. And so that repeated real root is just minus c over 2m. That's our repeated real root. And in this case, we have y is equal to c1 plus c2 times t times e to the minus c over 2m times t, just by some stuff that we've done in previous videos. Okay, so now I'm going to leave you guys with some warm-ups. So I'm leaving you with 3 warm-up problems. I'd like to point out that 1 and 2 represent undamped systems, whereas 3 represents a damped system. So I'll read through these, but you could also just pause it and read them for yourselves. So let's start with the first one. So a 10 kilogram mass stretches a spring 30 centimeters at equilibrium. Then we want to suppose that a 2 kilogram mass is attached to the same spring, initially displaced 25 centimeters below equilibrium, and given an upward velocity of 2 meters per second. Let's find the displacement function y of t, the frequency, period, amplitude, and phase angle, based off of what we did at the beginning of the video. Okay, so for the second one, let's suppose that a 2 kilogram mass stretches a spring 50 centimeters at equilibrium, and the system is at rest when an external force with forcing function 8 sine 4t is applied. Then find the displacement function y of t. So here there's no external force. In number 2, there is an external force. So for number 3, we're in the imperial system of measurement instead of the metric system. So a 64-pound object stretches a spring 4 feet at equilibrium. It is damped with a damping constant of 8 pounds times seconds per feet. And then the object is initially displaced 18 inches above equilibrium and given a downward velocity of 4 feet per second. And then once again, find the displacement function. And that's a good place to stop.